Hi, this is segment 4 of the Module 2 lectures. In this segment, we're going to talk about summarizing data from a quantitative variable. And now, numerical data can be discrete or continuous, as we saw in Chapter 1. Data from a numeric discrete variable, it may be more appropriately summarized in the same way as a qualitative variable, because the categories of a qualitative variable are discrete, just as discrete data. However, numeric discrete data can assume many categories corresponding to integer values, and since these values can be used to perform arithmetical operations. Therefore, you will find that typically if a numeric discrete variable has many categories, it is often treated as a numeric continuous variable. And you will see some examples in the book. The example that we will have in a minute, even though it's a continuous variable, is rounded up to an integer number, and we treat it just as if it were a continuous variable. So I'm mentioning this because it's perhaps a fine point, but it's important to notice that. All right, so and another thing why I say that is because now I'm going to talk about summarizing continuous data, but be mindful that the discrete numeric data can be treated in the same way. All right, so an important aspect of a continuous variable is that it can assume any value in an interval. Here's an interval of prices for an item. And I put that right here, and you can say that that's about $387 in this case. But you could extend the number of decimal places to which you specify the price. So you can say, well, this item is $387.2378 whatever dollars. So depending on how you decide to measure the unit or your ability to measure the price, you can extend it to any number of decimal places. And that's that's why I say that a continuous variable can assume any value in the integer. And I'm referring to a value with an infinitesimal number of decimal places. So because of that, the construction of the frequency distribution for continuous data is done differently, in the sense that we are going to partition the range of values for a particular continuous variable into what we call classes or bins. And then once we have those classes or bins defined, then we count how many of the values in the data set fall within each class or bin. So what I'm going to go through next is a procedure to create the frequency distribution for continuous data. All right, we're going to use this example where a manufacturer of an item wants to know at which price this item is being sold by retail customers. To do that, they survey 25 different retailers and find the price at which they're selling this particular item at. So you see there are 25 observations, and for each observation corresponds to one retailer. And here's the price that the retailer is selling this item at. And if you notice these prices, the price has been rounded up to an integer value of dollars. So this item is being sold at $401. All right, so now we're going to use this data and we're going to create the frequency distribution for this data. And then later in the next segment, I'll show you how we can display it graphically. All right, the very first step is you scan your data set, then you find the smallest and the largest value in the data set. So the smallest is $371. The largest is $412. Once you have that, then you calculate the range. So you subtract the smallest value from the largest value, and you see that the range of values is $41. All right, with this information, we proceed to step 3, and that is to determine the number of bins or classes. I'm using the word bins because, for example, Excel calls them bins and other software packages call them bins. In our book, they are called classes, so either one is correct. So that there are multiple rules to determine the number of bins. One common rule is just take the square root of the number of observations. And because this is simple enough, we're going to use that in our example. So to determine the number of bins, we take the square root of 25 because we have 25 observations, and that says that we should have 5 bins. Then in the next step, we determine what is called the row bin width. So to do that, we take the range and we divide it by the number of bins. So it's 41 divided by 5, and that gives us $8.2. So each class or each bin is going to has a width of 8.2 units. Now, using this, it's not easy to do calculations with a number like that, and that's why we call it the row bin width. So what we do is the actual bin width, we just simply round this number up to a convenient number. Remember, you always round it up. And that's because when you devise the bins, you will always encompass the larger value or the largest value in your data set. So we're going to round this up to 10. And this is just for pure convenience. You can round it to 8.5 or round it to 9 or 9.5. But 10 is pretty easy to handle. And you will see that in a minute. Once you have the bin width established, then you select a convenient value smaller than the smallest value. The smallest value is 371. And we select the lower boundary to be 370. Why? Well, because 10 is easy to add to 370, and I know that 10 plus 370 is 380. I don't have to get a calculator or anything to do that calculation. I can do it in my head. All right, so that's step 6. We select the initial lower boundary, and then we find what is called the upper boundary. And we do that by adding 10, the bin width, to the lower boundary value, and that gives me 380. Pretty easy to calculate. And then we continue to do this calculation of the lower and upper boundaries until the upper boundary exceeds the largest value, which is 412. So the lower boundary is any value bigger than 370 all the way to 380. The next class or bin is a value bigger than 380 all the way to 390. And you can see the difference between 390 and 380 is 10, the bin width. The difference between 370 and 380 is 10, the bin width. So I'm glad that we selected a bin width of 10 because it's pretty easy to add to the numbers. And we selected an initial boundary at 370. So the calculations are pretty easy to do. And then you continue adding 10 to the lower boundaries and then 10 to the upper boundaries. And now we use this bigger than because if we get a number that is exactly 370, well, that will fall in the previous boundary. But if it is bigger than 370, should be here. And we remember that we selected this number to be smaller than the smallest value in the data set. All right, so once we have these lower and upper boundaries, we proceed to calculate what is called the midpoint of the bin or the midpoint of the class. And to do that, we take the lower boundary plus the upper boundary numbers and divide it by 2. So if you do 370 plus 380 and the result you divide it by 2, you get 3.75. Or, I mean, you can see that the middle point is 3.75. That's exactly between 370 and 380. Then you proceed to calculate all the midpoints. Once you have that, then we proceed to now determine the frequency. So we're going to look at the data and see how many values fall within that bigger than 370 to 380. And so if you scan the values and you look for values that are between 370 and 380. So here is 374, that's bigger than 370, and is within the 380 limit. So that's one. You continue scanning And here's the other one, 371, which is the smallest value. So you have this, you have a frequency of 2 because 2 values fall within this range, or within this class, or within this bin limits. And then you do the same thing. Then you say, well, how many values fall within this class bigger than 380 to 390? And you can scan these numbers and you will be able to find 11 numbers. Then you proceed to the next class and you say, well, how many values fall within bigger than 390 all the way to 400? You will find 7. And the same for the next class, bigger than 400 up to 410, then you find 4. And bigger than 410, but smaller than, and up to 420, you only find 1 value. So this is the first part of the frequency distribution. And as before, in step 12, we're going to add the relative frequency and the percentage. And I say as before because we did the same thing for the frequency distribution for qualitative data. All right, so you sum the frequencies, and that should be 25 because we have 25 observations. Then you divide each frequency by 25, and that will give you the relative frequency. So you do that for every class. You get the relative frequencies, and if you add these numbers, you should get exactly 1. Then to get the percentage, multiply each relative frequency by 100, and you get the percentages. If you add these numbers, you should get exactly 100. All right, what does this mean? What does this table is telling us? Well, you can use the percentages, for example, and you say most retailers, 78% of them, sell this item at a price above 380 and up to 405. So if you look at these numbers, I used percentages from this class all the way to this class. So I just added these percentages, and if you do that, you get 78%. Also, only 2 retailers sell it at a price or below of 380. And only 1 retailer sells it at a price above 410. Again, this is my attempt to interpret the results here. You may see other interpretation, but the interpretation is based on the frequencies, the relative frequencies, and the percentages, and of course, the upper and lower boundaries of each class. So I'm doing this because in the exams, I will be certain to provide the table and ask you to interpret the results. You will see in the homework assignments that the Wiley Plus, the questions that they already have in their system, they're more focused on the calculations and a little less on the interpretation of the results. So in the slides, you will see me interpreting graphs, interpreting tables. And that I'm doing that because I will very, very deliberate in the exams and in the quizzes, which are the practices for the exams, where I present a table, a graph, or something like that, and then I ask you to interpret that table or that graph or that statistic. Okay, this is this segment, the end of this segment, and I will continue with another segment in the next recording.